Hello, everybody. Happy Monday. Everyone's so happy to be here. It's always refreshing. So, anybody have any questions or Pearson issues before we start? None that anybody's already emailed me? Okay. One thing about this class, Chemistry 161, is you can really kind of get lost in the math and like lose what's really chemistry. I mean, chemistry, study of matters, changes. It's very, very useful. So chemistry, even in Hawaii, the investment into chemistry every year is in the billions of dollars. So, and because whenever you study matter, you're studying chemistry. So chemistry is just a huge investment. Many people do it. Many people don't even realize that they're doing chemistry research. If you look at other sciences like astronomy or physics, actually physics does have a pretty high investment because it's useful, but like high energy physics, like the Large Hadron Collider in France and Switzerland, that's a couple $2 billion investment into that. And we spent an equivalent in our, relatively small state here in Hawaii on chemistry. Why is it not big news that we spend money on chemistry? Because it's useful, right? Studying high energy physics is not immediately useful right now. Astronomy is not immediately useful right now. So because of that, there's a huge amount of outreach. You'll rarely see outreach in chemistry because there's not really any need to. So, and because of that, you guys are all required to take this class, and then you can get stuck in like, okay, let's just do the math and balance equations and calculate moles. So, but there are some cool things about chemistry, and so we left off, we're talking about atoms, we talked about atomic theory, and we talked about elements. I have a few here, as requested. So, and I brought some rings. People wanted to see my meteorite ring. This is my meteorite ring. I'll come around, you can see it. So, 3 elements here: titanium on the outside, nickel, iron. You can see the 2 phases on it as well. So, 3 elements, if you will. And I picked these rings. You can get them in titanium and platinum. And I picked titanium because the titanium will corrode, and it's called a anodic protector, a sacrificial anode. The titanium will protect the nickel and the iron and prevent it from corroding. The platinum ring will go the opposite way. It'll force the iron nickel to corrode, and it'll rust the iron more quickly with a platinum ring. And I also have a platinum ring right here. Well, it's 95% platinum. This is my wedding ring. I don't wear it very frequently. So, and I also have this right here. I was trying to see if I have some silicon, I think, because silicon's kind of cool. But this is, because it's a crystal but it looks shiny. This is another metal. This is bismuth. So I'm picking the ones that are safe to touch. And another one that I'm keeping on me very closely. This is 24 karat gold. So here's pure gold. So you can feel some of these, and I'm going to walk around with them.
Don't trust us?
Well, I'll tell you what. You can. Oh, gold and platinum. But it's in care of my iPad too. Ooh, we can watch a song too. Why not? Is this thing? Let me see if is the sound up on this thing? Let me. Here's the Element song.
There's antimony
arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercury, molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered.
Yeah. You feel the gold. It feels really heavy. So, of all the metals, well, the one that I'm passing around is bismuth. It's this one right here. So, it's pretty. So of all the metals, so here's gold. Gold has that, of course, yellowish color. So most elements, I can see that the titanium, the bismuth, and the platinum, they all look about the same. I mean, you can touch them, they feel differently. Right? So you can clearly see that the platinum ring is a lot more dense. And if you can see the pure gold is also pretty dense too.
Why do certain elements like bismuth have that geometric pattern and just like color?
So question, why does some elements have geometry? You're talking about zero-S?
Yeah, well, it's got a clear pattern versus.
Oh, the cubic?
Yeah.
Oh yeah, it's a cubic structure. So some of it depends on how it's grown. So bismuth has a relatively low melting point. You see the melting point there is 271.3. You can't see it there. It's 271.3 Celsius or 520 Fahrenheit. So when you cool it down, you can get this a little bit more of a set crystal structure versus something like platinum. And platinum's a really high boiling points here. Our melting point has got 3,200 Fahrenheit. So when it cools down quickly. Yeah. So the filter, when I take it off and don't wear it, I don't like wearing it. You know, I like to lift weights and just scratch it up, and I wear it around my father-in-law who's mad for me. So then when he stops visiting, or I stop visiting him, then I'm like, "Where's my ring?" And the first day I'm like, "Oh my gosh, I got a ring!" Kind of comes and goes away. But here's platinum. I mean, this one, I guess it's not really a crystal structure. It's just, you can see this one's it's very amorphous, so really randomized structure for platinum. Okay. So some of the things about the elements. So this first column to the left. So like lithium, sodium, potassium. So these elements are called the alkalis. So the far left there, those are called the alkalis. And the reason why they're called alkaline, is that if you throw them into water, they form bases, meaning the opposite of acids. So that's platinum, gold. So, and like an alkaline battery, right? So an alkaline battery versus a lead acid battery. So alkaline batteries are alkaline in the center. And a lot of the names of the elements come from the alchemists. So the alchemists, they believed that you could take lead and turn it into gold. Well, you can, but you have to use a particle accelerator. You can't use just plain old benchtop chemistry to do it. So, but if you know Harry Potter and the first book, The Sorcerer's Stone, it's actually really the Philosopher's Stone. So, I don't know, I think that they did it because Sorcerer's Stone sounds better to Americans or something like that. But the alchemists looked for the Philosopher's Stone, and if you were pure of heart, you could change lead into gold. And I'm not a member of this, but there's a fraternity called Alpha Chi Sigma. That's the chemistry fraternity. And their initiation ritual is all about alchemy and turning lead into gold. They make their initiates carry around a bunch of lead for all night long or something like that. And as they get closer and closer to being initiated, they have to carry around more lead. So, I meant to mention about the elements also. Copper is weird. It has this copper color. Most elements have silver colored. Osmium has a slight bluish tint to it, if you see this. But it's the oxide layer. Same thing with potassium. Potassium has kind of a blue-purple sort of color to it, and it's the oxide layer. So all the other elements, though, they're all silver colored. So at least the metals. They all look about the same. Okay, but so alkalis, the metals there on the far left, alkalis are very reactive, extremely reactive, and they all form +1 ions. Next column over, the alkaline earths. So why are they called alkaline earths? So alkali metals are very, very water soluble. Alkaline earths make lots of precipitates. So those are salts that fall down in solution. And that's the good old earth, wind, fire, water. So the alchemists were like, okay, these are alkaline. It's not acidic, it's basic, it's alkaline when we find these metals and we put them in water. But then we mix other stuff with these elements. Stuff falls down, that's earth falling out of water. These are alkaline earths. So that's where the term alkaline earths.
Where's that from?
This is bismuth.
Where's it from?
It's rocks. Do you want to guess what the number one use for bismuth is? Pepto-Bismol.
No way.
Pepto-Bismol is the biggest.
Oh, of course. It's
Yeah,
small.
bismuth is the biggest supplier of it. I worked as a consultant. Lead bismuth is it's a really low melting point. Are you done with these? So lead bismuth has a very low melting point, and I was working on a project to recycle used motor oil using a metal bath as a heat exchanger. And so they made these huge blocks of bismuth, and I stole a little piece of one. One fell and it broke apart, and I'm like, ooh, I'm gonna grab that because it looks cool. So, and also bismuth is extremely safe. It's on the list of things that you can eat in infinite quantities. So, like the FDA has a list of chemicals that are that are considered completely safe. Things like aspartame, for instance. So that's a sweetener, and bismuth is one of them. You can have them in infinite quantities. Of course, you shouldn't eat that. It'll scratch out the inside of your stomach, but got my gold. All right, so these are alkali metals. They all form +1 ions. These are alkaline earths. They form +2. And I'm going to say a lot of things at the beginning, and I will say them over and over again throughout the semester, so you don't have to write this down and memorize everything right away. But I've noticed that about this book. I imagine I'm a student reading. Have you guys been reading the book? You're like, oh crap, I have to know everything right away. So you don't really have to know that just yet. But because there are things that are our future chapters that talk about things more in depth. And one of them is the periodic table, and specifically the quantum mechanical model of the atom. Explains much more why the periodic table is the way it is. So But we typically the periods of the rows and the columns sometimes referred to as families or groups because they have very similar chemical properties. So alkalis have very similar chemical properties. They all form +1 ions. These form +2 ions. And if you look at copper, silver, gold, they all are very similar, but they're not very reactive. So my ring, I passed around this one right here, it's platinum and palladium. So it's 95% platinum, 5% palladium. So it's actually two elements for the price of one here. Okay, and then moving over here, we have what are called the halogens. So fluorine, chlorine, bromine, iodine. So these form -1 ions. These are also very reactive. Halogens, it's a Greek word meaning salt forming. So it forms salts. There are two definitions for the word salt. One is the result of an acid-base neutralization reaction. So acids have certain properties. Acids taste sour. Like if you've ever drank vinegar before or eaten a lemon, you're like, that's sour. That's an acid. You're tasting acid. Bases taste bitter. Okay, so bitter melon are actually acidic. I tried this out. I was like, bitter melon, is this actually acidic or basic? I used it in some pH paper. It has a pH about 5 or 6. Almost every single food has a acidic pH. So bitter. So like, have you ever bought like cheap NyQuil or cheap Robitussin? You ever like the stuff they don't sweeten? Because I'm cheap. I'm like, I can just go to Walmart and buy Waltussin. You know, that's the stuff that I go for. And you ever take that stuff, you're like, what is that? That's bitter. Okay, that is the true bitter flavor. And humans, we hate the bitter flavor because most things that are bitter are also poisonous. So caffeine is bitter, so coffee is a little bitter. Caffeine is extremely toxic. So how much caffeine is in a cup of coffee? Somewhere between 50 and 100 milligrams, depending on the coffee. And 50 to 100 milligrams, that's nothing. That's a very small amount, right? So a teaspoon of salt is on the order of 10 grams. So if you had 10 grams of caffeine, your heart's going to pound through your chest. So caffeine, nicotine, those are both alkaline. Those are very, very toxic. So we tend to not like those, the flavor. So acids taste sour, bases taste bitter. What does salt taste like? It's salty. It doesn't taste sour, it doesn't taste bitter. It's something else. It's chemically different than an acid or base. So and salt is, when we say salt, we usually mean sodium chloride salt. That's the result of hydrochloric acid and sodium hydroxide. So, but other definition of salt is a nonmetal plus a metal that's not an oxide or hydroxide. That's the other definition of salt. So halogens make salts, and they make them very quickly. And they're all negative. They all form typically -1 ions. And then over here, the other group that we name are the noble gases. They used to be called the inert gases, but then we got them to react, and now we call them the noble gases. And noble is like the British. It's more British English. Like the commoners, the peasants, they're very reactive. The nobles, they are very proper. So like, this is the best day of my life. No, this is the worst day of my life. I'm so noble, you cannot tell. So that's the noble gases. They don't react very much. And if they do, you know, it's such a strange occurrence kind of thing. And why are the noble gases so unreactive? It has to do with their electronic structure. So their electronic structure is such that it's just really stable. So the halogens will end up gaining an electron. So as you move to the right, there's more electrons. The halogens gain an electron to be more inert. The oxygen family will gain 2, so these tend to be -2 ions. Nitrogen and phosphorus tend to gain 3, so these tend to be -3. Then over here, lithium, sodium, potassium, these tend to lose 1 electron. to be like helium for lithium, and sodium lose 1 to be like neon. So these tend to lose 1. These tend to lose 2. So the alkaline earths tend to lose 2 electrons and form +2 ions. And everywhere else, it's very complicated. We tend not to teach the reason why it's complicated here in this class. That's in future classes. It has to do with some of the finer points of the quantum mechanical model for that. So, and carbon, if you're wondering, carbon can either lose 4 or gain 4. It can go either way. Carbon, I think it personally tends to gain more than lose more, but it can go either way. Oh, we just did a whole barrel roll. Okay, so where's the periodic table? There we go. So to illustrate this without the pretty pictures spinning around. So these here form +1 ions, alkali metals, alkaline earths +2. These form -1s, the halogens. These tend not to react, and the noble gases. Oxygen tends to form -2, nitrogen, phosphorus -3. And this in the middle just kind of depends. So, and here's a step ladder. I was hoping to find some silicon. I think I mentioned that. Yeah, I did, but I couldn't find it before class. Let's see if I can bring it next class. I can show you a picture of it, but it's not the same as touching it. And you feel how heavy the gold and the platinum were? Those are very heavy. The densest elements are down here. Rhenium and osmium are very dense. So then these elements tend to be very dense too, the ones right next to them. So platinum and gold are very dense, but not as dense as rhenium. And so not as much of a good example, but we can use lead in bullets. And some of the green bullets use tungsten. So, but tungsten is much more expensive. So we tend to use more lead. Okay, how are we doing? Anybody have any questions? Okay, so periodic table. And so a review from last class. The chemical symbol is really redundant with the atomic number in the bottom. So Z is typically meaning the charge, and atomic number, number of protons. Mass number is number of protons plus the number of neutrons. And so to give you an idea, so, well, before that, do you guys like The Simpsons? I like The Simpsons, although it's getting kind of old. Anybody know what the name of the baseball team is? No one knows. Oh, Isotopes, the Springfield Isotopes. And where does Homer Simpson work? Nuclear power plant. So it's something to do. And they have the Bohr model on their uniforms. So it's something to do with nuclear stuff. So isotopes are nuclear. And so neon, for instance, neon has 3 isotopes and ratios. And here there's neon 20, and you can't see that as well, especially with the glare on the screen. Oops, that's too dark. This says as neon 2010 like this. So this is neon 2010, this is neon 21, neon 22. Neon 20 has 10 neutrons, 21 has 11 neutrons, 22 has 12 neutrons. So those are known as isotopes, and they are more or less chemically indistinguishable from each other. They're very hard. It's very hard to separate isotopes. You have to do it by mass. They don't chemically react any differently. So argon isotope has a mass number of 40. How many neutrons does it contain? So argon is here. Argon has 18 protons. So 18 and then 40. So how do you figure this one out? It's just 40 minus 18, and that means it's 22 neutrons. Now, the next idea are ions. I mentioned ions when I was talking. Ions are atoms. So an atom means neutral charge. So saying a charged atom is an oxymoron. That means it's two things that are opposite each other, like a smart dumb guy or something like that. That's an oxymoron. A charged atom is an oxymoron. Atoms are neutrally charged. Ions are from atoms gaining or losing electrons. A positive ion is from a loss of electrons, is known as a cation. And if you have a hard time remembering that a cation is positive, think of the T as a plus sign. Negative ions are anions. That's from gaining electrons. How do you make something negative? Gain electrons. It does not involve addition or subtraction of protons. If protons are changed, the element's identity changes. So the difference between this element and this element is that gold has one more proton. Okay, so how many electrons are present in the O2 minus ion? Oxygen, if you look at the periodic table, oxygen is element number 8, and it has 16.00. So 8, the top number is the atomic number. So the minus 2, so we have 8 electrons plus 2 because of the minus 2, which means there's 10 there. And I already mentioned these, the predictable charges. I didn't talk about aluminum, but I've already mentioned these, that the elements that have predictable charges. So the halogens all form plus or minus 1. And you notice, I guess I didn't talk about this, hydrogen's in 2 spots. We have a positive ion, a negative ion over here. In my mind, hydrogen tends to form more positive ions than negative ions. Although you can get negative ions with hydrogen. Not an issue here. The issue for corrosion is here. You can get a type of corrosion called hydrogen embrittlement. That's when you have typically iron, and if it's just sitting there, it can get hydrogen forming inside of it and form iron hydride. And the issue with iron hydride is when you heat it up, the hydrogen is released. And we tend not to have heaters here because we're in the tropics, it's so hot. But in the mainland, in certain places, most places, especially in the olden days when they would use radiators, where you'd heat up water and put water through places, the boiler would sit there for a while, and then so summer and fall, or spring, like end of spring, summer, then fall comes around, it starts to get chilly, all right, time to start turning on the heater, and they start heating up the boiler. Hydrogen would be released, and sometimes it would explode, and it's because of hydrogen embrittlement. It's easy fix for hydrogen embrittlement. You just have to electrically ground it. If you electrically ground your iron, it will not embrittle. But they didn't figure that out until a little bit later. But hydrogen's kind of both places. And I didn't even mention that it was an alkali metal. Hydrogen's not an alkali metal. At least it's not considered. It's in the family, but it's not considered an alkali metal. We believe that there may be a metallic phase for hydrogen. We think that it's in really high pressure. We haven't observed it yet. We think it might be in Jupiter, for instance, but we've not observed the metallic hydrogen at least not on Earth for certain. We don't have any direct proof for it yet. Okay. And what about chemistry, elements of life? So I mentioned astronomy. This is a big push for astronomy right now. We're looking for life. And specifically, one of the things we're looking for is oxygen. We're trying to find, oxygen is in O2 gas. When we find that, we think that we have found life. But it has to be enough oxygen. The planet Mercury, 35% of the atmosphere of Mercury is oxygen. But it's really thin. So it's not that there's life on Mercury, it's just it's so close to the sun is baking the rocks and releasing oxygen that way. Okay, so here are the elements of life. So what are we made of? So if you look at it by mass, we're mostly oxygen. And by atom, we're mostly hydrogen. Why is this not surprising? Yep, H2O water. If you look at that, we're about half water-ish, right? Maybe a little bit more. But that doesn't mean that all the H2O, all the oxygen and hydrogen is bound up as water, but quite a bit of it is, right? So sweat, blood, cytoplasm, lots of water in our bodies. So, and we're said that we're carbon-based life forms, but we're not, if you look at carbon, we're not even 1/5 carbon by mass and 1/10 carbon by atom. So why carbon-based? Carbons are really weird elements. So like when you get to the elements, like the rare earths, I mean, they more or less look the same. It's hard pressed to see what the difference between the rare earths are. They have different magnetic properties, which you use them for electronics. So that's important. But carbon is just really, really strange. What's strange about carbon is that it forms straight chains. It all has 4 bonds. It's bonds of 4. And also, if you let it by itself, it tends to form straight chains of things. So I used to do research with carbon. And if you throw a bunch of carbon into a vacuum chamber, it forms chains. So if you compare it to silicon or germanium, so carbon, silicon, germanium, all in the same family, silicon forms kind of football structures up to about 19 atoms. And after 19 atoms, it kind of forms these kind of blobs. If you throw 20 carbon atoms in a chamber, it forms a chain. And that's important because of life. So our DNA, it's a bunch of chains there. Our cell membranes are phospholipid bilayers, typically on the order of 25 carbon atoms long. So our cell membranes are 25 carbon atoms with hydrogens, another 25 carbon atoms here with phosphates on each end. So a lot of our life structures are from carbon, from the backbone of carbon there. Silicon-based life forms would not be like us. At least you wouldn't have structures like DNA or cell membranes. So silicon can be a kind of well, if you look at sci-fi, like, oh, that's a silicon-based life form. As a chemist who studied it, it would not be like us at all. The structures would be completely different. So, but these 4, oxygen, carbon, hydrogen, nitrogen, we sometimes, especially if you follow the astronomy, they refer to this as CHON, C-H-O-N, because that kind of looks like a word. There's nothing special about it. It's just, it's something easy to look for. We're looking for CHON, kind of thing. But why all these? Because those are used to make proteins. So the most common amino acids, with the exception of cysteine, has sulfur in it, but the rest of them are just carbon, hydrogen, oxygen, nitrogen. So there's sulfur and cysteine, but the rest of them, proteins at least, just have those 4. And calcium, we have a bit of calcium, but not as much. Calcium's in our teeth and our bones and also in our bloodstream. So same thing with phosphorus. So bones actually originated as metal stores. So bones, we more or less, we strip down our bones. Of course, we think of our bones as our structure, right? I'm knocking on the table. That's our bones. We have structure with that. I mean, we keep them, of course, we have our endoskeletons to protect our organs and be able to move around. Well, we move around with our muscles, but I mean, we have a lot of our structure comes from our bones. But originally, bones and steel is our primary thing, is a metal store, electrolyte stores. So astronauts that are in space, they lose lots of bone density. So the body just strips down the bones. So our bones get stripped down and replaced very, very frequently. So, and if you've ever broken a bone, I mean, it can take a while to heal, but it's not like spraining your ankle. I've sprained my ankle a few times. Like bones heal really quickly, relatively quickly to like a ligament or a tendon. If you've ever had tendonitis or a sprained ligament. The reason for that is there's blood flow that goes directly to bones. And not only that, our body uses bones as our metal stores, so they get exchanged very quickly. So bones can heal very quickly. So calcium, phosphorus, and there's a little bit of other things like cobalt and cobaltin. It's a B vitamin, for instance, but But this is what our body is primarily made of. If you wonder what we are made of. Okay, and I didn't swear. Any questions? So next thing is atomic mass. So if you look at the periodic table, and you can't see this. Okay, and I can't zoom in on this one. Maybe I should. No, I don't have that. Oh, that one doesn't have the atomic mass. Shoot. Okay. So if you look at the periodic table, though, and I know that especially people in the back, so I'm looking at phosphorus. It has 30.974, and in your mind, like, okay, that's like 31. And you look at hydrogen, it's 1.008, good enough. Lithium is 6.9, that's kind of about 7. Then you get to something like copper, and copper is 63.546. So what is going on there? Why do we have things that are so far away from a whole number? Well, the bottom number on the periodic table is the weighted average of the terrestrial means here on Earth, atomic masses. So if you look at chlorine, for instance, chlorine here on Earth, chlorine is about 75% chlorine 35 and about 25% chlorine 37. So because of that, chlorine is 35.45. If you look at chlorine on the periodic table, the atomic mass is 35.45. That's based off of about the 3-to-1 ratio here. And silver is almost 50-50, 107 and 109. And another element that's 50-50 almost is bromine. Bromine is almost exactly this much. It's almost 50-50 as well. So, and that's just here on Earth. So the Earth being terrestrial, terra, the Earth, terrestrial average. The American Chemical Society just released a new periodic table, and it gives ranges. So rather than it says now that we can see perturbations in this. We have enough resolution. The atomic mass is somewhere between here and here for these elements, depending on where you're at. So, and why is the Earth so strange? What's so special about it? Well, we believe that the sun is at least a third-generation star, meaning that there was a Big Bang that formed a star, that supernova, that formed another star, that one supernova, and then formed the sun. So we're at least a third-generation star. But we have other elements too. So things like platinum are formed from the collision of neutron stars, so like pulsars slamming together can form platinum and gold and these types of things. So there's obviously different sources for the Earth, at least the elements in the Earth. So it's not just from stellar dust. There are other elements that have formed other places. So we have a wide range of things. And also the terrestrial averages. So the elements we have, all 118 of them, they're the same throughout the cosmos. So if we go to the Andromeda galaxy, that's a galaxy that we're in a collision course with. If we go there, we're going to find the same carbon, hydrogen, oxygen, nitrogen. Same thing. It's going to be exactly the same as here on Earth. But what could be different are these averages. So that's why, like, you ever see these things like, oh, this meteorite is from Mars. Like, how the heck do you know it's from Mars? Because we know it's not from the Earth because of the isotope averages. We look at the moon rocks. So we actually did go to the moon, and we brought moon rocks back, and they're different than the rocks here on Earth. At least the averages here on the isotopes of them. Okay, but let's do this for that one. Copper has 2 naturally occurring isotopes, 63 with a mass of 62.9291 atomic mass units, relative abundance of 69.17%, and copper 65 with a mass of 64.9278 atomic mass units and abundance of 30.83%. What is the atomic mass of copper? So the way you would calculate this one is, so it's just the weighted mass, And the percentages, so 69.17, this is 0.6917 as far as numbers. So let's look at this. So the atomic mass is the weighted average. It's 62.9291 times 0.6917 plus 64.9278 times 0.3083. And if you're wondering where I'm getting these numbers from, color coding them for you. So the mass 62.9 with the 69% there, the first one. Mass of 64.9 times the 30% mass there. And you throw it in your calculator. I might cheat and look in the book. So much easier than throwing it in my calculator. In chapter 2, not chapter 1. Oh, here it is. And this equals 63.5456 to 3 sig figs. Like that. Okay, so recap for this one. 2 isotopes of different masses, different abundances. So we take the masses, we multiply them by the abundances, we add them together, and then correcting for sig figs, we get the atomic mass of copper to be 63.55. Questions with this one? Okay, next question is, why is copper 62.9291? Why is it not 63.0000000000? Why is it that number there? That's referred to as the mass defect. So if you look at the binding energy versus the atomic number, it looks like this. And the top of the chart here is iron. Helium is kind of a peak there. But so if you start off with hydrogen and you fuse it to form helium, that's extremely exothermic. It releases energy. So matter will turn into energy there. And then nuclear fusion releases energy until you get to iron. And iron, specifically iron 56, so that is the most stable element. The protons and neutrons in these elements going up, they lose mass, and protons and neutrons are the lightest, they're the least massive when they're in iron. And after iron, nuclear fusion is endothermic, it absorbs energy, and then these protons and neutrons become more massive. So this is important for a few reasons. So nuclear fusion is exothermic to iron. Nuclear fission, breaking apart atoms, is exothermic from any elements heavier than iron going over. So that's the reason why we use very heavy elements like uranium and plutonium to fizz, to break apart and form energy. And the fact that iron is heavy, this is what causes what are known as type 2A supernova. So if you have a big star about 3 times or more massive than the sun, it can form, it has enough gravitational pull, it can form iron in its core. So our sun doesn't have enough matter. It can't form iron. The highest the sun, we believe, will ever go is to form carbon. So, but the other stars can form heavier elements, and when iron starts to be formed in the core, what happens though is that when iron fuses, it absorbs energy. And when you have a gas and you absorb energy, what happens? The gas shrinks. So when enough iron forms in the core of a star, the core will shrink really quickly, which puts more pressure, which causes more nuclear fusion, which causes more energy to contract it more fusion, and then that inward shrinking, so that causes a shock wave. It implodes, then it causes a shock wave going out, the explosion. The shock wave going out then lights the whole star up, and that's a type 2A supernova. So it starts off with the shrinking of the core from the iron, shrinks it down, causes the shock wave going out, and the whole star balloons up in a very big light show. So, and if you look at the Earth, the other reason why we think that the Earth is at least a third generation or more from the Big Bang. If you look at the Earth, if we were alien exoplanet, whatever, scientists, we would categorize the Earth being it's a mostly iron planet with a silicate crust and mantle. So the core of the Earth, the outer core, inner core, it's somewhere between 100% and 80% iron. So if we were to look at the Earth itself, it's mostly made of iron. So we live in an iron planet. Of course, on the outside, the crust is mostly silicate, so silicon, oxygen, and other stuff. So mostly magnesium, calcium, and aluminum other than that. So, but mostly silicon and oxygen here on the surface. Okay. Now atoms, we are very tiny. So maybe I'm showing my age, but I won't even ask this question because I'm sure I'll get very few responses. Right when I turned, I guess I was 22, I went to Vegas for the first time and I could gamble legally. And if you play in the slot machines, you have a bucket that actually fills with quarters. And you take the bucket and when you cash out, you bring the bucket to the person. I mean, like, I'm not gonna, that's enough laundry for like 15 years. I'm not gonna use all those quarters. So you bring your bucket of quarters to the front desk, and what do? They weigh it, right? So they figure things out by mass. So same thing with things like M&Ms, right? No one's going to count all the M&Ms. They figure out how many M&Ms are in a bag by weighing them. So assuming that they're all the same relative size, we can figure out how many M&Ms there are. So atoms are very tiny, and how do we count them? We count them by mass, and we use this concept we call the mole. The mole is from a guy, his name is Avogadro. And we still use this idea that 12 grams of carbon-12 is a mole. So that's what we have it based off of. The mole, Avogadro's number here is, I don't know if this made it is 6.02214 times 10 to the 23rd. This is a big number. Let me illustrate. One more, okay. That's Avogadro's number. So those are zeros, not sixes. So tell you two things. You're like, that's a huge number. That's the first thought. Second thought is, man, atoms are tiny. So we have this huge number to deal with something like this. So we can get around atoms being tiny and we have this bigger number to deal with this fact. And we do this for other things too, right? So paper is one of them. Like we use terms like ream. A ream is 500 sheets of paper. I don't go to someone, hey, can I borrow 1,500 sheets of paper? Like, can I get 3 reams, please? Right? Or you can even say a case. Like, hey, can I get a case of paper? You're like, I gotta make a bunch of copies for all my classes for the next 3 years. Like, can I get a case of paper? So we take something smaller where the case is like, I think it's 12 reams or something like that. So that's 6,000 sheets of paper. So we typically don't even think like, okay, can I get 6,000 sheets of paper? Like, no, can I get a case of 12 reams of paper, please, for paper? So you can count. We take numbers like things that are small and we put them to other things. So that's they call the chemist's dozen. Although a dozen is not exactly that big. I mean, 12 is not a very big number. Okay, so let's do this for some time to do some boring math. Calculate the number of copper atoms in 2.45 moles of copper. So 2.45 moles copper, and then times 6.02 times 10 to the 23rd Cu atoms per mole of copper. So the moles of copper cancel. And what do we get? We get 1.48 times 10 to the 24 copper atoms. So this one here, we have 2.55 moles. How many copper atoms is that? So it's multiplying over. It's like if I have 3 dozen eggs, how many eggs is that? Well, it's 3 dozen eggs times 12 per dozen. That's 36 eggs. So how many copper atoms are 2.45 moles of copper? 2.45 moles. Avogadro's number per mole, that many atoms. So then you see here 10 to the 24, 1.48 times 10 to the 24. Big number. 14 with 21 zeros after it. Or 15, I should say, the 2 signals. Questions with this one? Okay, lead is not lead. It's actually, pencil lead is not lead. It's actually carbon. Calculate the amount of carbon in moles in 0.0265 grams of pencil carbon. So 0.0265 grams of carbon times moles of carbon. And to figure out where this is, if you go to a periodic table, in carbon, you probably can't see this in the back, but carbon, it's 12.011. So you look at that bottom number. 12.011 grams of copper. And you're thinking, wait, I thought carbon was the standard, that we do everything based off of carbon. Carbon also has isotopes too. It's about 1 or 2% carbon-13 and a very small amount of carbon-14 radioactive carbon. And then this is 2.21 times 10 to the minus 3 moles of carbon. And notice a few things, that we're just writing things in moles and we're putting numbers in front of it. So, and we had, well, I guess the previous one was atom. We had 10 to the 24, but now we have 2.21 times 10 to the minus 3. So these numbers can be big and small. In chemistry class, they're usually pretty small. If you go into biology, they're even smaller. So if you ever do biological research, I've never done a biological research, but getting, like when you look at proteins, you'll look at things like in the nanogram, something really small. So, and then if you do things in industry, you're talking about thousands of tons of stuff. But chemistry class, so millimoles, so this would be 2.21 millimoles. Sometimes you call it millimoles. Get things in very small quantities. Okay. Oh man, okay. So an aluminum sphere, okay, combining things. Aluminum sphere contains 8.55 times 10 to the 22nd aluminum atoms. What's the sphere's radius in centimeters? Okay, so now we have to do some problem solving. What's our given information? We're given the number of aluminum atoms, and we're given the density. So how can I go to radius? So the From the atoms, I can figure out the number of moles. If I know the number of moles, I can figure out the mass. And since I know the density, if I know the mass, then I know the volume. And then I know that from the previous section, the sphere is 4/3 pi r cubed is the volume. I can then solve for radius and go backwards there. So it's a multiple step problem. I even look at this, I'm like, oh man, time to think. Okay, so I want to get to, so the first step, I want to get to volume. So then I'm not given here is the volume is 4/3 pi r cubed. So, which means radius is equal to 3v over 4 pi cube root. So I know that, so next thing I need to figure out the volume is. So volume, so start off what we know on the left, 8.55 times 10 to the 22nd aluminum atoms. Actually, maybe I don't have enough room here. Down. So then mole of aluminum over 6.02 times 10 to the 23rd aluminum atoms times, gotta look at the molecular mass, the atomic mass of aluminum. It's close to 27. What is aluminum? It's 26.982. 2 grams aluminum, 2 mole aluminum, and then we need to have cubic centimeters. So centimeters cubed per 2.70 grams aluminum. So look at the units. Atoms cancel, moles cancel, grams cancel, left with volume. Right. And in doing so, that's weird. Why is that fuzzy? Okay, doing that we get 1.42. My Apple Pencil is getting fuzzy. Here I am shaking it like it's a pen. So 1.42 cubic centimeters. So then we take this and we plug it into there. Then radius is equal to 3 times 1.42 centimeters cubed all over 4 pi cube root. And doing so, we get 0.697 centimeters. Like so. So don't worry, we're not going to be solving problems involving spheres this entire class. It's just the first 2 chapters we're doing this because it's an easy way to show a quick. Do you have a question or are you confused? Okay. You're also going like this. You ask a question. Okay, so remember, attack the problem. So we have an aluminum sphere, this many atoms. What's the sphere's radius? There's a density. So, okay, what things do I need to know if there's a problem? Like, well, I need an equation. I don't know what the equation is. In this case, the equation will be the volume of the sphere. Because why would you think that? Well, because using these data here, you can go from aluminum atoms to a volume. And then you got to find a way to relate volume to radius. And if it's a sphere, it's going to be the equation 4/3 pi r cubed for the volume of the sphere. And then for here, then we're using dimensional analysis. So number of atoms, the mole, to get the number of moles of aluminum. And a mole of aluminum is 27 grams. And then the density, divide by the density. And why do we need to divide by the density? Because of the units. So keeping track of the units. And going so, you get the volume, put the volume in the equation, and then get 0.7 centimeters as your radius. So questions with this? How to do this? Okay. All right, on to chapter 3. And we won't get very far into this. I know we got 15 minutes of class left. So let me do some of the general kind of talking stuff. So maybe if you notice, I tend to kind of start out a chapter by talking a lot, and then I start to go into the math, and then the last part is kind of wrapping everything together. So we're getting to the talking part. So talk about chemical bonds, the things that tie us together. So let's say you have a 3-person report, and your job is you need to categorize chemical bonds. And if you're the first one there, say, I pick metallic. That is I'm wrong. Ionic. Pick ionic first. Pick ionic. That is by far the easiest. Ionic bonding is very easy to understand. Positive and negative charges attract. So unlike charges attract, like charges repel. So if you know Coulomb's law is the force is equal to a constant times the charge of one and the charge of second over the distance squared. So that's Coulomb's law. If you know Coulomb's law, you can do that to calculate the attraction or repulsion. That combined with the Pythagorean theorem, that you can use that to figure out anything you want to know about ionic bonding. That's all there is to it. It's Coulomb's law and Pythagorean theorem. So you do those and do that over and over and over again, and that's ionic bonding. It tells you exactly how strong things are. It tells you what happens. What if I just remove an atom right here? What's going to happen there? They've already calculated that. We've thought of that already. So what if we had an atom here in this spot? Like we've already calculated that too. So lots of people done that. And there's a shortcut too. You can learn something called, if you take chemistry your junior year in organic chemistry, there's something called the Madelung constant, which is just the Pythagorean theorem averaged over a crystal structure. So that's the easiest. The second easiest is metallic bond. Metallic bond is a sea of electrons. This requires a little bit of quantum mechanics, but if you do something, it's something called the local density approximation. If you assume that the electron is just a gas, that's just this constant gas everywhere. If you calculate a metal, saying like, okay, we have a bunch of positive centers, then we have this negative cloud that surrounds it. If you do the calculations, you can more or less, that describes things very, very well. That's called the local density approximation, and you can calculate most properties of metals doing that way. Why do you want to calculate properties of metals? Why would you have this be 95% platinum and 5% rhodium? Because the rhodium makes it stronger. It's an alloy. You do these calculations to look at alloys. Things like what they put on fighter jets, like in the engines. Like, okay, well, what kind of properties do we want in this fighter jet engine? Like, all right, let's talk to some chemists and physicists and do some calculations first before we start doing stuff for the engineers. So metallic is like a sea of electrons. And then covalence, which we'll get into a little bit, and we'll cover most of the semester on sharing of electrons, especially when we get to the later part of the semester. So here is my two-dimensional representation of an ionic bond. So the positive and negative charges are close together, and they're far, but they still feel like, so these negative charges and these positive charges, they have a repulsion, but they're closer to the unlike charges. So the net effect is that this thing is held together because these are closer. There's more attraction here than there's repulsion here, and vice versa. So what happens if you take a hammer and you smack? Has anyone done this before? Like salt? Have you ever pounded salt before? It's an insult. Go pound some salt. No one's ever done that. What about a rock? What happens if you hit a rock really hard? What happens to the rock? It breaks apart. If you just move it down by one atom, suddenly these are repelling. That's going to crack. You're going to form a crack in the ionic compound just by moving it by. All you have to do is move it by one atom, and you can break it. What happens to a metal, though? What happens if you have your car and you go up and you take a hammer and you smack the hood of your car with a hammer? What's going to happen? You dent.
The progressive people show up.
Yeah, progressive shows up, and so here is my metal. We have the positive nuclei with a sea of electrons. What happens if I move these atoms down by one? Does this break the bond at all? Nope. It's still metal. It's still working. So ionic compounds tend to be very brittle, meaning they break easily. And metals are very ductile. That means bendy. You can take iron. You can bend iron if you're Superman, right? So you can bend things, bend metal. It's fine. It doesn't really do anything. What happens if you take an ionic compound? So something like, you don't see like weights made of salt, because if you try to pick up a bar made of salt, it'd probably break in your hands. Because if you just put a little pressure on it, it snaps it right apart. So also why we put rebar in concrete. Concrete is calcium carbonate. It's an ionic compound. The bendiness makes it much stronger with the steel. So with my limited artistic ability, here is some prettier pictures. So here is sodium metal, and there are your sodium atoms, and there are electrons flying around there. And then this forms sodium chloride salt. So, well, without looking at it, which one's the chloride? Is it the bigger one or smaller one? It's the bigger one. So electrons, electron cloud. What happens when you add negative charge to something that's negative? What's going to happen to it? Is it going to get shrink or is it going to get bigger? Get bigger. Negative charges don't like each other. They expand. So the slant idea, though. So all biological surfaces are negatively charged. So if you get stung by a jellyfish, what are one of the things you should do? What should you put on a jellyfish sting? You put something acidic. Why? Adding acid adds positive charge, it shrinks things. Adding negative things, a base, will swallow it up. For jellyfish stings, though, the best thing you're supposed to do now, the latest research, well, that's initially, if you have like tentacles on yourself, use something acidic like vinegar. So people say use urine. Urine has a pH of about 6. Vinegar has a pH of 3. It's logarithmic, so vinegar is 1,000 times stronger than urine. So it'll work, but vinegar will work a lot better. And that's just to close the stinger cells, and then you remove the tentacles, and then add heat. So specifically as hot as you can handle. So I had the pleasure of being stung by a stingray one time. And I was a weird one. I got stung on my hand. I got stung, actually, this finger. It was after one of the hurricanes in Florida. I was helping my dad clean up his house. He lived in Florida at the time. And they have a nice silica sand in Florida, and I was going around. I like the feel of silica sand in my hand, and I was just doing yard work. I was covered in like mulch and sawdust from using the chainsaw. So I'm like, okay, instead of showering, I'm just going to jump in the ocean. And I was playing around in the sand, and I found a nice baby stingray, and it stung me on the finger. That hurt. That really hurts. and I could feel the venom was tingling going down my arm. It was one of those, oh crap. So I went home and I looked up what to do, and they said, go see the doctor. So I went to the urgent care clinic. But before that, I guessed, I was hypothesizing. I'm like, okay, the venom is probably protein-based, so I can denature the protein, change the shape with heat. And so what I did was I heated up some water, and I put a metal spoon in the water. Metals have very low heat capacity, so you can get a lot of heat in metal really quickly. And my dad probably thought I was crazy because he was the one that drove me. But I'm like, all right, give me some hot water and a metal spoon. He's like, all right. And that'll make you feel better, son. You know, and so I'm sitting there in the car, and I'm like, ah! Okay. Ah! I put the spoon back in the water. Ah! You know, and after I did it 3 or 4 times, it did feel better. Because the metals, you can get really hot, and you can apply a lot of heat. So like, let's say I put my finger in a boiling water. That would be a bad idea, right? So you take a metal spoon, though, you can apply a lot of heat in a very specific spot, which will still hurt, but it'll neutralize the venom. It'll denature it, at least change the shape of the protein. Of course, some of the venom already went in my bloodstream, but I survived. But okay, all right, back to anticompounds. Sorry for the random story. All right, so anticompounds, and some things when we talk about structures, talking about compounds. So if you see this, I have calcium and OH2 in parentheses. That means that I have 2 of whatever I have in the parentheses. So it's like calcium and the calcium plus 2 ion, then plus of these 2 of these OHs, and they're minus 1 charge to cancel out the plus 2 charge. Anybody on a diet before? I guess everyone knows. What do you call sugars, starches? What kind of food are those? It's not fat, proteins, it's carbohydrates. Why do we call them carbohydrates? This is glucose. This is sucrose. And this looks like it's C6H2O6. So, and sucrose, table sugar, is like C12H2O12. That's why we call them carbohydrates, because it looks like it's carbon and water. Carbon, hydrates, water. So these, though, carbohydrates, they're not really hydrates. Hydrates actually have water stuck in them. So a hydrate means that you have water stuck in there. If you take the lab, you're going to do the Epsom salts. So look at Epsom salt. That's a hydrate. It's magnesium sulfate 7 hydrate. To give you the answer, if you don't know it already, you can look it up though. And this is still the beginning things. We're gonna go into talking about molecular formulas and what they mean, and what kind of information we can get from them. So empirical formula is the lowest ratio. So benzene here is C6H6. Acetylene is C2H2. Acetylene is what they use for blow torches, for the welding torches. Benzene, it's a liquid. It's very smelly. We tend not to use it anymore because it's pretty heavily carcinogenic. But they both have the symbol, the empirical formula is CH, but they're 2 very different compounds. So we're going to do some calculations to find empirical formulas, but keep in mind, though, that you can get various different compounds from that. Glucose, already mentioned, CH2O. CH2O is also formaldehyde. And I can tell you formaldehyde is very different than glucose. I'm sure you probably know that. Glucose tastes delicious. Formaldehyde smells really badly. And here's ammonia here. So I think, did my alarm go off? I think it's time to go off. Oh, 2 minutes left. Okay. I think I'll end there. You can get a minute of your life back. Anybody have any questions? No? Okay. All right. See you on Wednesday.